The aim of the experiment is to measure constant velocity using Tutor timer and Tutor tape. The apparatus is a trolley runway with leveling screws, 12 volt AC, 50 Hz power source, connecting leads, Tutor timer, Tutor tape, sellotape and a ruler. The precautions for this experiment are to clean the runway with methane spirits to remove dust, dirt or anything that may cause friction. These wheels have special bearings, so you don't need to be oiled. The Tutor timer produces 50 dots every second. Test to see whether the trolley goes at a constant velocity. It is travelling at a constant velocity if the dots are equally spaced. Ignore the first two dots and start by drawing a line on a dot, then count 5 dots ahead and draw a second line. The distance between the two lines is 6.6 centimeters. We'll take a 5 dot interval further down to see if we get the same length. Draw a line at a dot, then count 5 dots ahead and draw another line. The distance is 5.7 centimeters. These dots are closer together than the first dots. This means the trolley is decelerating due to friction. We are going to use the force of gravity to compensate for the force of friction by tilting the runway. We need to use copies to tilt the runway a little more. The dots are now equally spaced so we can measure constant velocity. We'll draw our lines, but this time on a 10 tick interval. The distance is 12.6 centimeters. The average velocity of the trolley will be the magnitude of the displacement over the time. The time taken for 10 dots is 10/50ths of a second, or 0.2 seconds.
distance time graphs are graphs which plot distance against time. That sounds a bit obvious, but anyway, interpreting them can be slightly more difficult, and I do think it's something worth knowing about. Now, I could show you a graph like this, but first, let's get our head around the axes and how they're labelled. Well, we've got the horizontal axis, which is the one across the bottom, and it's also known as the x-axis, and this is labelled as time in seconds. Then, of course, we've got our vertical axis, which is the y-axis, and this is labelled as distance in meters. Now here we've got a journey, and it's got 4 different sections or legs. So let's start with the first leg, and that starts at 0, 0 and travels along to 550. Now, by drawing a triangle on the graph, it can help us see a bit more clearly what's going on. So we can see that we have travelled 50 metres in 5 seconds. And from this, we can actually work out the speed, because speed equals distance divided by time, or S equals D divided by T. And since the distance is in metres and the T is in seconds, that means that the units for the speed will be metres per second. So let's have a look at this first leg of the journey, and we can see that it's 50 divided by 5, and that gives us a speed of 10 metres per second. Right, let's have a look at the second leg of the journey. Now this starts at 550, and if we go along, it finishes at 1075. So that means the distance travelled is 25 metres, and the time taken is 5 seconds. So the speed will be 25 divided by 5, 5 metres per second. Okie doke. The third leg. Well, this starts at 1075 and finishes at 1275, which means the distance travelled is nothing. Oh dear. And the time taken is 2 seconds. So that means our speed is 0 divided by 2, which is 0 metres per second. And this means that we're not moving anywhere. Whenever you see a flat horizontal line like this in distance time graph, it means your speed is 0. You are staying put. Right. Well, I could show you more about this graph, but I don't think that's as fun as getting Dave off his backside, breaking a sweat, and getting in his own distance time data. And that's why I've sent him off to Queen's School in those weird shorts.
Here we go. Hi guys, you here to help me with my challenge?
Yeah.
Yeah, who's got the instructions then?
Yeah. You need to read this and we'll do some warming up at the same time.
Some warming up?
Yeah.
Okay. Today I want to see how good an athlete you are. Are you a sprinter? Are you a long distance runner? Or are you a couch potato who spends too much time stuffing his face with crisps and chocolate? Chocolate or stretching? Chocolate, definitely. Once you've finished your warm-up, you'll be going to run 200 metres.
Oh, against Izzy.
Right. Then 1500 metres.
Oh, and that'll be against Andre.
And I'm going to compare you against the students using distance time graphs. And by the way, you're not stretching hard enough. How can she possibly know?
Come on then, do this one.
Where's my chocolate?
Three, 2, 1, go.
3, 6, 9, 12, Nearly. Yes!
You ready?
Yeah.
Okay, let's go.
I'm already winning. How you doing, Andre? Yeah, I'm fine. Yeah. Feel a little burn already. It's just a warm up. Yeah. You go ahead. Yeah, alright. And I'll catch you up. Yeah.
Oh dear, Dave. That's not going to impress anyone. But hopefully the graphs will tell a different story. Let's have a look. Let's have Izzy first. And the beginning of the race starts at 0, 0. And then we can see after 6 seconds, she has travelled 12 metres. After 15 seconds, she has travelled 75 metres. After 33 seconds, she has travelled 183 metres. And she's run her 200 metres in 39 seconds. That's pretty good. Let's see how Dave's done, and let's plot his graph on the same axis. Oh dear. Well, you can see that after 6 seconds, they've travelled the same distance. But after 15 seconds, he's only travelled 57 metres. And if you look at the graph, you can just see how far Izzy, that's the purple line, is in the lead. Looking at these graphs, it looks like the race is lost between 15 and 33 seconds. Now, Izzy's average speed during that time can be found from this graph. We can see that her distance changes from 75 to 183 metres, and her time changes from 15 to 33 seconds. So that means she had travelled 108 metres in 18 seconds. So, take 108, divide it by 18, and we get an average speed of 6 metres per second. Let's see how Dave was doing during the same period, and we can see he travels 72 metres in, again, a time of 18 seconds, and that gives him an average speed of 4 metres per second. Well, let's have a look at the distance runner Andre. Maybe Dave's done a bit better against him. As Andre's running further, we just need to have a different scale on our axis. And let's have a look. Andre's this top line. So we can see that it's actually split into 4 main sections. The first section runs from 0 seconds to 100 seconds. Then we've got this second section, which is from 100 to 200. And he's actually slightly faster there than he was in this first section. Then we've got the third section up here, which is from 200 to 250, where he's a bit quicker still. And then in the final section, in this final 100 seconds, his speed actually decreases a little bit. Right, so how's Dave done? Well, oh dear. We can see that he gets slower and slower and even slower until he's practically crawling at the end. I'm going to have a word with him.
How did I do?
Well, you're obviously not a sprinter, so let's just forget about that one. But when it comes to long distance running, your start is slower than Andre, your speed in the middle is less than Andre, and you can't keep on running for as long as Andre. So to be honest, it's fairly pathetic.
Thanks.
But you never know, you might be better on the rowing machine.
A row machine? I'm going to be so much faster than you. We'll see. We'll see.
Okay, Dave, this is a straight race between you and Phil. 500 metres, you ready?
Yeah. You ready? Okay. 3, 2, 1. Doggy paddle. Alright. Winner. Yeah. Nice one, Phil. Well done.
Oh, it doesn't look like Dave is much of a rower either. And I bet the graph shows us that as well. So let's have a look at Phil's first. Let's have a look at his distance time graph. And we can see that in the first leg of his journey, he has travelled 200 metres in 50 seconds. And that's at a constant speed of 4 metres per second. And moving on to his second leg, he has travelled 300 metres in 50 seconds. And that's a constant speed of 6 metres per second. And let's compare that to Dave's. Let's have a look. Oh dear, Dave. Well, we can see that in Dave's graph, he's got 2 sections that are straight lines, and neither of these are actually as steep as Phil's. So it's pretty clear that Dave was slower throughout the race. Now that is what too many crisps can do to you.
Okay, you started slower, you travelled less distance, and you didn't even finish. You are pathetic, man.
But I was faster.
Now, how can you be faster and still lose the race, Dave?
Have a look at the graph around 1 minute, and I bet you I was going faster than Phil was.
All right, I'll take a look, but I think you might be wrong.
Right, well let's have a look at how fast Dave was going at about a minute. At a minute, that's 60 seconds, which is this point. And at this point, the graph is a curve. So what we need to do is place a tangent on this curve and find out where that tangent is the steepest. Now, if we draw a right-angled triangle onto our tangent, that means we can find out the speed at that point. Now our triangle joins the coordinates 60, 60 and 100, 320. And as you can see, the triangle has a height of 260 meters and the time is 40 seconds. So we can use the speed distance time formula to work out the speed. So that's 260 meters divided by 40 seconds, and that gives us 6.5 meters per second. Now let's see if Phil was ever going faster than that. Oh, well, his fastest speed was 6 meters per second. Incredibly, Dave was actually right for a change. Amazing.
Right, I've got some news for you. At 1 minute, you were rowing faster than Phil. In fact, it was the fastest that either of you travelled at any point in the race.
Yes.
I told you I was faster than you.
Alright, on your bike.
Sorry?
You know, get on the exercise bike, let me beat you.
Oh no.
So what do you need to remember about distance time graphs? Well, the steeper the graph, the faster the object is moving. And remember, if there's a flat horizontal line, then the object is not moving at all. It's still. To work out the speed of an object, you need to draw a triangle so that you can look at the change in distance and the change in time over that particular section. And to work out the speed, of course, you use distance divided by time. So in this case, we've got 100 divided by 20, which gives us 5 meters per second. But if you've got a curved graph, you can always find the speed at any particular point by drawing a tangent onto the graph and then working out the gradient of the tangent. And the point where the tangent is the steepest, that is where the object is going fastest. But if it's Dave, don't expect your tangent to be that steep.